Okay, so let's start. Hi, everyone. We're very happy to start the new year in HoloTube. Please check out our web for the program for this semester, which I think is quite interesting. And so we're very happy to have today Tian from the University of Chinese Academy of Science, who will tell us about solitons and non-equilibrium physics in holography. So please go ahead.
So thank you. Thank the organizers for the invitation. And so the topic I'm going to talk about is the solitons and non-equilibrium physics in holography. So this is the outline. So first, I'll give a brief introduction to the background and motivation of this talk. And next, I'll discuss the superfluid instability and superfluid dynamics, where we can see solitons. We can see solitons play a very important role in such dynamics and instability. Then we discuss superfluid solitons themselves and their instabilities. And finally, some concluding remarks. So first of all, let me review a little bit the history of solitons. Solitons were discovered early in 1843 when Russell observed a traveling soliton in the Union Canal in Scotland. Actually, such a soliton is just a bump on the surface of water. And such kind of solitons were modeled as the solutions of this so-called KdV equation later. And this equation is actually an integrable model, and it admits exact solution of this form. So this is just the soliton observed on the surface, water surface, and this soliton keeps traveling at a constant speed c. Actually, this kind of soliton has been studied extensively, and later on, solitons were found in various kinds of systems, such as the nonlinear optics, and the Bose-Einstein condensates, and so on. And among them, the one that is most closely related to this talk is the soliton in the Bose-Einstein condensate. Actually, as well known, a weakly coupled Bose-Einstein condensate can be described by the Gross-Pitayevsky equation. If we set the mass parameter equal to 1/2 and turn off the external potential, this GP equation is just of this simple form. And this is just like a Schrodinger equation, but with an extra nonlinear term. So sometimes it's called the nonlinear Schrodinger equation. And here the coefficient G is the coupling constant of this nonlinear term. Actually, the physical meaning of this G is the effective self-interaction of the scalar field psi. And if G is positive, this effective interaction, self-interaction, is repulsive. And in this case, this equation has the following exact solutions, this family of exact solutions. And here, the simplest case is beta equal to 0. So in this case, this I beta term is just vanishing, and this factor is just 1, and as well as this factor. And this time dependence also drops out. So in this case, this wave function is just a tangent function of x, roughly speaking. And so it's just the kink-like configuration. So it is called a black soliton because the wave function is just 0 at the center of this soliton. And if beta is non-zero, this wave function is essentially complex. It's not real. And in this case, this soliton moves at a constant speed proportional to beta. And because it's non-zero everywhere, so we call it a gray soliton. And if G is positive, which means the self-interaction is attractive, we can have bright soliton solutions to this equation. And the simplest example of such bright soliton is of this simple form. And the bright solitons can also travel at a constant speed, but I didn't write down the explicit form here. Okay, solitons can also appear in relativistic models, such as lambda phi 4 theory. For such a theory, the equation of motion is very similar to the GP equation. So it is not surprising that it can also have such black soliton solutions. And because of the Lorentz symmetry, this solution can be made traveling just by a Lorentz boost. Okay, so any questions so far? Okay, so the big question is why to study solitons? So I listed 3 reasons here. The first one is they are very simple objects, but they are also quite non-trivial. So it's a very ideal object in physics. And the second is they play an important role in non-equilibrium physics, in particular in superfluids, which is just one of the main topics in this talk. And the last one is they themselves have very interesting dynamics, which is another main topic of this talk. And because we will consider soliton configurations in holography, so another question is why should we do holography or apply the ADS-CFT? Because I think most people here are familiar with holography, so I think I should be very brief here. So from my perspective, I just focus on 3 problems that should be solved for quantum many-body systems. And the one that I want to emphasize is the first problem, the non-local equilibrium problem. That is, if we consider quantum many-body systems out of local equilibrium, then hydrodynamics as the most useful effective theory for quantum many-body systems cannot be used any longer. And actually, one of the examples is just the soliton configuration, because soliton is a small-scale object, and so hydrodynamics is not expected to be held in the neighbor of the soliton center. So, so this is a key point.
Sorry, sorry to interrupt. Can I ask a question?
Yeah.
So I guess I would like to distinguish between being out of equilibrium and being outside the regime of applicability of hydrodynamics.
Mm-hmm.
Would you agree with that distinction? The reason I'm saying this, for example, is suppose you consider a phase-separated configuration where you have 2 phases coexisting at the critical temperature in some system with a first-order phase transition.
Yeah.
Then the interface between them is not necessarily well described by hydrodynamics because you have large gradients.
Exactly.
But nevertheless, this is an equilibrium configuration.
So by the equilibrium, I mean not only in time but also in space. So yeah.
But
you know what I mean. So
would you say that liquid water and ice cubes sitting in the water
at the interface, it's not equilibrium. It's out of local equilibrium, right?
Why? It's time independent.
It's time independent, but the equilibrium is not only for space, not only for time, but also for space.
But the temperature is constant. You can define a temperature and it's constant everywhere, including at the interface.
Yeah, temperature is well defined everywhere, but not for many other thermodynamic quantities.
But you seem to be identifying equilibrium with homogeneous, and so this is an inhomogeneous configuration I'm talking about, but it's still in equilibrium. The two phases coexist. They have the same pressure.
So here I just want to emphasize local equilibrium, not global equilibrium.
Yes.
I mean, yeah. So the whole system could be in local equilibrium, but not in global equilibrium. So it's not homogeneous, right?
Yes. So I'm saying that these inhomogeneous configurations can be in local equilibrium.
Right.
But yes. Okay, it seemed to me you were identifying. So you would call a phase-separated configuration out of equilibrium, even if it's sitting
at the interface, near the interface, it's not equilibrium, not in local equilibrium. So that's what I mean.
Okay.
So maybe that's just a definition. Okay. Yeah. Okay. And another two problem is strong coupling problem and the dissipation problem. I mean the time arrow problem. So it's not easy to describe the time irreversible dynamic process of quantum manifold systems from first principles. Okay. So here comes holography, which is a novel way to construct the effective field theories, actually dealing with these problems with one extra dimension. So I just mentioned very briefly how holography works for these problems. So actually for the first problem, we holography just provides a dynamic description of this boundary quantum system that is more complete than hydrodynamics, at least more complete than hydrodynamics. And the strong coupling problem is solved by the so-called strong weak duality, and the dissipation or time arrow problems solved by black hole formation and creation. Okay, so here's are some examples of quantum manifold systems far from equilibrium. The first one is the well-known quark-gluon plasma produced in LHC, and at the early stage of this QGP production, there is no local equilibrium, so hydrodynamics is not useful there. And the second example is the superfluid dynamics, say in helium-4, and the superfluid dynamics generally involves vortices which break local equilibrium in the same reason as solitons break local equilibrium at the center. And so these examples both have holographic models which go beyond the hydrodynamic region. And there are also other examples that are more controllable in experiments. For example, the superfluid vortices in Bose-Einstein condensate and optic lattices. These examples provide a lot of opportunities to test the holographic approach as illustrated in those papers. Okay, so now let's discuss the superfluid instability and the superfluid dynamics. and see the role played by solitons. As is well known, superfluid, the superflow is unstable if its velocity is greater than a critical value, namely Landau's critical velocity. Landau argued this point by examining the dispersion relation of elementary excitations under Galilean boosts. So actually, if the velocity is too large, the superfluid becomes unstable because the excitations can have negative energy. But the very important question is, what is the final state of the superfluid if Landau instability occurs? Will the superfluidity totally break down? So this question cannot be answered by Landau's argument because this argument only works at the linear level. But to answer this question, we need to have the full nonlinear dynamics of this superfluid. So for this reason, we should use holography to see if we can get the answer. So before we consider the full nonlinear dynamics of superfluid, so let's first consider the Landau instability at the linear level. So in holography, elementary excitations correspond to linear perturbations on top of the box spacetime and also the background matter fields. And because we want to consider the superfluid at finite temperature, so we need a black hole in the dual bulk ADS spacetime. And the linear perturbations of the bulk black hole systems are just described by the quasi-normal modes. So in this way, we can describe the elementary excitations of the boundary system. And effectively for stability analysis, we can only consider the dominant mode among all the quasi-normal modes. The dominant mode is just the quasi-normal mode that has the largest imaginary part. So if the dominant mode is stable, I mean its imaginary part is negative, then the whole system is stable, and otherwise the system is unstable. So we need a holographic model of superfluid to consider the full dynamics, and the simplest example of such model was provided many years ago in this paper. And so the action, I think many people are familiar with this model. So yeah, we just go very quickly. So the action is just a charged scalar field coupled with UN gauge field in the bulk. And the bulk spacetime is just a Schwarzschild ADS black-green. And to make our life easier, we just ignore the backrashing of the matter field onto the bulk spacetime. So the bulk spacetime is just fixed as this Schwarzschild ADS black-green under the Eddington-Finkelstein coordinates, because we want to do dynamic evolution of this spacetime, of this system. And its Hawking temperature is just due to the temperature of the boundary system by holography. And the ADS conformal boundary is located at z equal to 0 in these coordinates. And near the boundary, the gauge field and the scalar field have these asymptotic behaviors respectively. And by the so-called ADS safety dictionary, the coefficients in the expansion of the scalar field, phi and psi, are just a source and the condensate of the superfluidity respectively. And if we don't drive this system, we should turn off the source phi to see if there is non-vanishing condensate psi. And another conjugate pair of thermodynamic quantities is provided by the expansion of this gauge field A, which is the particle number and particle number density and the chemical potential. The particle number density is just the time component of the conserved current, the boundary conserved current due to this U1 gauge field. And for this system, there is scaling symmetry, actually because of the conformal symmetry of the ADS spacetime. This symmetry is actually unwanted if you use this model to describe a real superfluid. Actually, you can break this symmetry by constructing some more complicated models, but we didn't bother to do so, at least in the study of Landau instability. Because of this scaling symmetry, the temperature T and the chemical potential mu themselves are not observable. So just this scaling invariant ratio is physically observable. And this system is known to go through the normal fluid, superfluid phase transition. Yeah. Excuse me? Any questions?
No, I think it was just some noise.
Okay.
But if anybody wants to ask, just reiterate. Sorry.
Okay. So if we lowering the temperature across a critical temperature TC, or equivalently, if we increase the chemical potential mu by the scaling symmetry, then this system goes through this phase transition. From the gravity side, it's just a about black hole, carry black hole transition. And on the boundary, it's just the normal fluid, superfluid phase transition, which is second order because of this, because of the spontaneous breaking of the U1 symmetry. The next question is how to make the superfluid flow along, for example, the X direction. Actually, you can only you can just assume the wave function or the condensate to be this plane wave form of a wave vector k in the X direction. And gauge equivalently, you can set the boundary gauge field AX to be minus k and keep the wave function psi a constant. And actually, the second way is more convenient usually. And the velocity of this flow is given in terms of the current J, just defined in the same way as in quantum mechanics from this wave function or condensate. And this is the gauge invariant definition of the velocity, which can also be recast as this form in terms of this boundary gauge field and the argument of the complex scalar field style. And at the linear level, the instability of this superflow has been analyzed in this paper. So this is just the cosinormal mode of analysis, as we mentioned before. And so here, in this plot, we only show the dominant mode on top of this superflow with various velocity. So the different curves in these plots correspond to different velocities of this background superflow. And the left is the real part. And if we just look at the imaginary part on the right, so we can see that if the velocity, the background velocity is greater than some critical value, just like these curves, there is a certain region, there is a certain range of the wave vector k that the dominant mode is unstable, right? Okay. And so as we know, the superflow is unstable if it's too fast. Then what will happen? What will be left eventually? Actually, the authors of this paper conjecture that there should be a striped face left behind the instability, and because the most unstable mode is at a finite wave vector k, right? So they conjecture this, but we answered this question in this paper, and actually we give a different answer. In the simplest case, in 1D, we have a Soliton generation, and actually the system will go through a transient turbulent state, and finally and eventually in holographic superflow with a velocity lower than the critical value will be left. And in the 2D case, we first see Soliton generation at the flow direction, and then because the Soliton itself is unstable, as we will explain a little further shortly, it has the so-called slink instability, and so which will lead to vortex generation. So the system will go through a 2D transient turbulence, and eventually a homogeneous superflow with a velocity lower than the critical value will also be left. So we don't have time to go into any detail about the numerical evolution. So here I just list the full equations of motion for numeric sphere. As you can see, we have defined a field phi, which is just related to the original scalar field by a scaling. This set of equations are actually very good for numerical evolution. And the result we obtain is just this. We illustrate this result by these two movies. So the left one is just the evolution of the absolute value of the wave function. And we can see the generation of solitons as the wave function. At certain places, the wave function will become zero at some moment. And the right one is the evolution of the superflow velocity. Here, I didn't show the critical velocity here. Actually, it's just near 1, I think. So eventually, this superflow has a velocity lower than the critical velocity. Okay, so let's move on to superfluid solitons themselves and investigate their instabilities. Okay, so any question about this? If no question, let's go.
Can you hear me?
Yeah.
Hi.
Trying to ask a question.
Yes, if I could ask a question about this. So this you're getting by numerically evolving these set of equations that you showed just a couple slides back. But what are the initial conditions that you put in order to see the actual nucleation of the solitons? Do you put them in your initial boundary conditions, or how does it work?
We just randomly perturb the original superflow. Yeah, a very tiny perturbation on top of this superflow. So the evolution.
You have the homogeneous superflow solution, and then you put
homogeneous superflow solution, and on top of it, we just put some very tiny perturbation. Yeah. Okay, is it clear?
Yeah, thank you.
I have, sorry.
If I may, one more question. So normally we expect that these solitons, they should be created as pairs, right? Solitons and anti-solitons?
No, not necessarily. Because here there is no conserved topological charge here, unlike the vortex case. For vortices, because the Wannier number is a conserved topological charge, so it can only be created pairwise. Yeah.
So this will be true in the 2D analysis that I guess you will talk about next. In 1D, you're saying solid created in pairs?
Yeah. You can see the pair creation of vortices later. Yeah.
And in 1D, solitons don't have to be created in pairs. Okay, I think I wasn't appreciating.
Yeah.
Okay, thank you.
May I ask also one question, maybe?
Yeah.
So I was wondering which ensemble are you using for your computation?
Ensemble.
Basically, yeah, basically, I like, is there any like conservation of energy in your, like total energy in your X direction, or?
Yeah, it's not, actually it's not easy to talk about the energy here. I think a well-defined quantity in the probe limit is the free energy. Because you just fixed the background geometry, but the energy should be read off from the geometry. You just fix it, so yeah. You know what I mean?
Okay.
Yeah, so actually the free energy here is decreasing, monotonically decreasing in this process, and you can think of the energy as conserved. Yeah, and the particle number is also conserved. The total particle number is also conserved in this system. Yeah, it's just the conserved current due to the U1 gauge field.
Okay, thank you.
Okay, so let's go. Now we will talk about the solitons themselves. So at the finite temperature, black solitons in holographic superfluids were constructed many years ago by these people, and the typical profile of holographic black soliton is of this form. Someone sent message in the chat box. It's obvious that you cannot define winding in 1D as there is no way to write. Yeah, is this the full question? I cannot.
You mean on the chat? No, just was just clarifying his question, that he agrees that there is no solitons in 1D. So.
Okay. Okay. So this is the typical profile of the condensate or wave function, and actually in holography, in addition to the condensate, there is also the particle number density. So we also plotted the particle number density here. It has a depletion at the center. So, well, as is well known, the black solitons are also unstable in higher dimensions. I mean, because black soliton is codimension 1 object. So in 1D, it's just a point light, and in 2D, it's just like a line, and in 3D, it's a wall. You can consider it as a domain wall. And so, for example, in the 2D case, the soliton has one transverse direction. So if you just bend it a little, this bending effect will be amplified and just like a snake. And eventually this soliton will break down into vortex pairs. And such instability has been extensively observed in experiments, just like in this paper. And actually, black soliton is also unstable even without bending or even without transverse direction, in particular at the finite temperature. And if you perturb, for example, just in 1D, if you perturb the black soliton a little, then it will deform and accelerate automatically, and eventually breaks down. And so just like in this movie. Okay, so can we analyze the instability of solitons? As we know, there are at least 2 kinds of instabilities. Can we analyze them in one framework? So this is the question we focused on. And actually, we can achieve this by introduce transverse wave vector along the y direction. So now the kink direction is the x direction. So and the y direction is translation invariant. So if we introduce such a transverse wave vector q in the y direction, when q equal to 0, this perturbation is y independent. So it can model the self-actuation. And if q is not 0, this y-dependent perturbation just lead to snake instability. So that's the idea behind our work here. And so, for example, if we just take a given q and calculate the Gaussian mode of the system, we will find one unstable mode here. So I will give a little bit detail about the calculation of the Gaussian mode on top of such homogeneous backgrounds, because usually Gaussian modes are calculated in the homogeneous background. By homogeneous, I just mean there is only one direction, actually the r direction, the radial direction of the black hole. And the other directions are just homogeneous. But now, because the background configuration is a soliton, it has another inhomogeneous direction x, just the kink direction, in addition to the z or r direction. So in this case, it is technically complicated. So we are better to use the evolution-like approach to calculate the Gaussian modes. I mean, just under the Eiding-Frankenstein coordinates. And the boundary condition are almost the same as the full nonlinear time evolution. So if you are able to do the full time evolution, you can calculate the Gaussian modes. And in the homogeneous case, we just illustrate the method in this paper. And now we just use this method to deal with the inhomogeneous backgrounds. And the second point is that the coordinate mode is just of this general form. Here, the big psi is just a collective notation for all the bulk fields. And we have these two conjugate modes coupled together because the system, in the system, the scalar field psi is coupled with its conjugate, its complex conjugate. And if we substitute this delta psi into the linear perturbation equation, then we will have this form of the homogeneous equation. And after this discretization along the inhomogeneous directions, that is z and x, this just becomes a very large linear system. Actually, you can get all the coordinate modes by a generalized eigenvalue problem. Okay, so in this way, we can just give some very interesting prediction, actually a prediction of a novel dynamic phase transition. By this, I mean, if you change the temperature or equivalently the chemical potential, then at a certain critical value, for example, for the temperature T is approximately 0.9 times TC. TC is the critical temperature of the superfluid phase transition. And you will observe that the most unstable mode go through a transition. Actually, if the temperature is lower than the value TD, the critical value TD, then the most unstable mode has a wave vector Q not equal to 0. So in this case, the dominant channel of the Soliton decay is the snaking instability. But if the temperature is higher than this value, then the dominant mode has vanishing wave vector Q, which means that the acceleration instability is dominant. So, so this can in principle be observed in experiments. And we also perform the full nonlinear evolution of this system. Yeah, maybe we can just wait a moment. Yeah. So you begin with Soliton. So in 1D, a Soliton is just a line, a straight line, and you put some tiny perturbation on top of it. Then this Soliton will decay. Depending on the temperature, it will decay in the snaking instability channel or the self-acceleration channel. And in these movies, the snaking instability dominates. So you see vortex pair generated here. And if there is if it's in the self-acceleration channel, you will not see so many vortices. Yeah. But how to characterize the dynamic phase transition more precisely? Actually, we can have this critical behavior of the dynamic phase transition as T approaching the temperature TD. Here, Qmax just means the wave vector of the most unstable mode. So the most unstable mode is of this form when approaching the temperature TD. Yeah, the gamma is a dynamical exponent. And actually this Qmax is essentially observable in experiments because we have argued that the vortex number density produced by this snaking instability is proportional to this Qmax. So we can measure the NV by experiments to verify this critical behavior. And in various cases, this exponent gamma is well fit by 1/2 numerically. And we also proposed a Landau-Ginsburg-like argument to describe the dynamic phase transition and obtain this gamma equal to 1/2 value theoretically. Okay, so and let me just very briefly mention some other Soliton solutions.
Can I ask a question?
Yeah.
So what's the intuition behind this statement that the vortex number is proportional to Qmax?
Okay, so yeah, it's maybe you can just yeah, you can intuitively say it from this movie, because the Qmax is the wave vector of the most unstable mode, so it will dominate. So it grows most quickly, right? And so it will make the soliton of the curvy form just determined by this wave vector Q. So yeah, eventually these nodes will become vortices. Okay, any questions?
So if I get it right, then essentially what you're saying is that this instability will always create arrays of circular arrays of solitons.
Yeah, because the Winding number is conserved. And eventually, yeah, go ahead.
When you heat them up, can you make them move? Do they unbind?
Actually, this movie is in an ideal state, because we just put one mode of perturbation. So it creates some vortex pairs that is equally spaced, right? But if in experiments or in more realistic evolution simulation, we put all kinds of perturbations on top of this Soliton configuration, then these vortices are randomly placed, randomly created. So eventually they will annihilate each other. So then the system will settle down to a homogeneous state. Yeah. Okay. So I mentioned very briefly some other Soliton solutions in holography. As we said before, there are gray solitons that move at a constant speed in the GP equation. But in holography, because we are consider a finite temperature system, because local structures moving in the finite temperature background will cause dissipation, as argued in this paper. So it's not expected that we can have gray Soliton solutions in holography at a finite temperature. And actually, we tried a lot to construct such solutions, and yeah, we cannot get any solution. So if we work at the 0 temperature, yeah, we don't have such a restriction. So for example, we can work in the ADS Soliton background, which is 0 temperature, which is no, there's no black hole. So we can construct the gray Soliton configurations also in the simplest holographic superfluid model. And this background is just a double weak rotation of the ADS black-green. Maybe I just skip the details. And a typical profile of holographic gray Soliton that we obtained is just like this form. And this is the condensate, the profile of the condensate of the gray soliton, and it moves at constant speed v equal to 0.6, and the condensate also has a non-trivial phase profile along the x direction, but yeah, we didn't put it here. Another interesting question is that can we have bright soliton solutions in holographic superfluids? I put a big question mark here because we don't know the answer. And so finally, some concluding remarks. The first conclusion is that solitons play an important role in superfluid instability dynamics, including quantum turbulence. But this actually this point is an ongoing project, so I didn't mention quantum turbulence a lot here. And the second point is that a superfluid soliton is itself unstable, which leads to interesting non-equilibrium physics, like dynamic phase transition. And there are also some open questions. The first one is how to characterize 1D quantum turbulence. Because I asked this question because in a classical system, a classical fluid, there is no 1D turbulence because the continuity equation just tells us that the flow is laminar, the flow is trivial. So it's homogeneous. So there is no turbulence. But in the quantum case, because there can be soliton generation, and the solitons are randomly generated, if we can have some criterion about what is a quantum turbulence in 1D, that's a very nice contribution to the quantum turbulence. And the second one is the bright solitons. We don't know if we can construct bright solitons in holography. For the gray soliton, because it's moving, it's traveling at a constant speed, and they can collide, they can interact with each other. So it has actually some authors have studied gray solitons, the dynamics of gray solitons in some other systems. So how about the dynamics in the holography? It's also an interesting question. Okay, so I think I will stop here, and thank you.
Thank you very much. Very nice talk. Very interesting. We had some questions, but we of course have time for more questions. So let's hear from the audience. Don't be shy. Just unmute yourselves and ask. Let's see. I might have a question if nobody asks. In any case, let me just remind everybody that after we end the recording, we'll open the floor for more informal comments if somebody has one. Okay, so then let me ask you a small question. How, when you show this instability, the instability there, the final state of the Landau instability, you said that to obtain that state, you have to like somehow seed the superflow with small perturbations, right, in terms of solitons. So how are you sure the final state is independent of how you do this, of the initial conditions, let's say, with perturbations?
Can you repeat your question?
So yeah, just the very first thing you showed, right? That there was this question about what happened to the Landau, to the superflow at the Landau instability. Yeah, mm-hmm. And I mean, I was very curious about that as an author of that paper you mentioned. So then you said you find that the answer is that solitons appear and the final superfluid velocity is lower than the critical. Mm-hmm. So yeah. My question is, so to arrive to that, I understood that you have to like somehow like perturb the solution with a lot of small solitons, right? Or how do you do it? Mm-hmm. And you do that randomly, or I mean, the question is, how are you sure that the end state doesn't depend on this perturbation, or on how you do the perturbation?
Yeah, I think I get your question. So
sorry.
Actually, the final state is also more or less random, yeah, depending on the initial perturbation. But I think because we don't do a very large system, I think if it's numerically accepted, yeah, if you do very large system, then I think the final state should be yeah, should maybe just a little bit below the critical velocity. Yeah.
By very large, but this should be equivalent to doing many realizations, not to like doing this many times and just averaging.
Yeah.
And by you said it's depending on the random initial conditions. You mean the velocity that you arrive to is kind
exactly.
of random. Okay.
Yeah.
I see. Thanks. Okay, let's see if there's more questions. I mean, we had some, but the idea of HoloTube is that everybody can ask as many questions as they want, until the speaker has to leave, of course. Okay, if there are no more questions, more formal questions, let's say we end here. So let's thank you, Tian, again for the very nice talk.
Thank you, guys.
Let me stop the recording.
Okay. Okay, goodbye.